In this video, we will be going over the AP Physics 2 Thermodynamics FRQ questions. Starting with the 2015 exam, students are watching a science program about the North Pole. The narrator says that cold air sinking near the North Pole causes high pressure. Based on the narrator's statement, a student makes the following claim. Since cold air near the North Pole is at high pressure, temperature and pressure must be inversely related. Do you agree or disagree with the student's claim about the relationship between pressure and temperature, and justify your answer? So this is a bit of a strange one to start off with. We are, where am I? Here I am. So we are starting off with having to justify based on the ideal gas law. The reason I'm saying that this one's a bit of a strange one, it is off of the 2015 exam, which is always a bit dated. Here we have what we would typically consider to be more of a checkboxy kind of question. So we have to disagree with the student's claim. The student is wrong. And we know that the student is wrong because of the ideal gas law. PV equals nRT shows that pressure and temperature are directly related. Assuming that the volume and the number of molecules are held constant. The reason that the Nature documentary made that claim was because while the pressure is increasing and the temperature is lower, the volume and number of moles are not actually held constant. It's a density thing. So the air molecules are getting more closely packed together, meaning that the volume is effectively decreasing. But that doesn't actually address the question. There is an alternate solution talking about density, but if we just remember our ideal gas law, we're good to go. Next part, we have the experimental design. We're trying to design an experiment to test this student's claim. Put a check in a blank next to each of the items that you would need for the investigation, outline the experimental procedure, and make sure that the outline contains sufficient detail so that another student can follow our procedure. So we're going to want a cylinder. Either we need to have a movable piston and then specify that the piston is held constant, or something with a fixed lid so that the volume is constant. We need to measure the pressure, we need to measure the temperature, and we need to have some way of changing the temperature. Here it is strongly encouraging you to go down the lines of a hot water bath or a cold water bath. So we have selecting one of the cylinders and implying or indicating that the volume is held constant. Selecting the equipment described with no extraneous equipment. We don't need a meter stick. We don't need a stopwatch. So you should not be checking those. Describing a method of measuring pressure that is at more than just two temperatures. And describing a method of measuring the temperature of the enclosed gas. So the example here is inserting a thermometer in the gasket, which it specifically said that they have gaskets through which instruments could be inserted. So we need to put the pressure sensor and the thermometer into those gaskets. I could also see you maybe measuring the temperature of the water bath, but you have to specify that the water bath is held at constant temperatures for a significant period of time to allow the temperature of the air inside the cylinder to reach equilibrium with the temperature of the water in the bath. And that's not so easy to do. So there were, I forget how many, 4 points in that experimental design. The next section, the sample below shows data from different experiment in which the volume, temperature, and pressure of the sample of gas are varied. We have to choose a subset of experimental trials that would be most useful in creating a graph. What we're looking for here are trials where the pressure and temperature are different, but the volume is held constant. So I would maybe say trial 2, trial 5, trial 8, trial 11, and trial 14. I would not go for trial 1, 7, and 12, simply because 3 data points are not enough to get a good trend. So there were 2 points there for selecting a set of trials in which the volume is held constant. and for selecting trials in which volume is 5 cubic centimeters and explaining that there are the most trials for this volume. So if I had selected that 10 cubic centimeter one, I would have just gotten the 1 point. I would have to select the 5 cubic centimeters to get the 2 points. Part D, plot the subset of data chosen. Plot the subset of data chosen in Part C on the axes below. Be sure to label the axes appropriately. Draw a curve or line that best represents the relationship between the variables. So here we're going to want probably a pressure versus temperature graph because we are changing the temperature of the water bath and that is affecting the pressure. We need to, for 1 point for plotting P versus T, 1 point for appropriately labeling your axes, and 1 point for a line of best fit. Make sure your axes are labeled. This is actually a bad example because the axis here is not labeled Kelvin. It needs to be labeled. Actually, I'm not even sure if it is Kelvin. No, it is Celsius. So make sure you label your axes. The last part is what can be concluded from your line. So we should be able to determine that there is a direct relationship between pressure and temperature. The next one was off of the 2016 exam. This one was using a PV diagram for an engine. 2 moles of monatomic ideal gas are enclosed in a cylinder by a movable piston. The gas is taken through a thermodynamic cycle shown in the figure above. The piston has a cross-sectional area of 5 times 10 to the negative third square meters. Calculate the force that the gas exerts on the piston in state A and explain how the collision of the gas atoms with the piston allow the gas to exert the force on the piston. There are 2 parts to this. We have to calculate and then we have to explain. The calculation is just a matter of using the definition of pressure, P equals F over A. So F equals P times A, and plugging in numbers. The explanation has to do with that the atoms colliding with the surface of the piston, those atoms have momentum. When they bounce off of the piston, they bounce off because there is a force exerted on them by the piston, therefore they exert a force on the piston. Part 2, calculate the temperature of the gas in state B and indicate the microscopic property of the gas that is characterized by the temperature. So this is using PV equals nRT to calculate the temperature for that given state, and then having some indication that temperature is related to average kinetic energy or average speed. Again, there's 2 parts to that. Calculate and indicate. Make sure you do both parts. Predict qualitatively how the internal energy of the gas changes as it is taken from state A to state B. Justify your prediction. So going from state A to state B, we have to indicate that the temperature is increasing. You'll notice that it said qualitatively, which means we don't use equations. So going from state A to state B, we're going to be on a higher isotherm. Remember, our isotherms are these inverse lines that run down. State B is at a higher isotherm. We have increased the volume while maintaining the same pressure by having the particles move at a greater speed. Therefore, they're at a greater temperature. So because the volume increases at a constant pressure, the temperature goes up. They did reference an equation here, but you'll notice they did not calculate. That's the important thing about qualitative understanding. You can reference the equation, but you really should have your explanation mostly in words. Part 2, calculate the energy added to the gas by heating as is taken from A to B to C. So we have to find the total energy added to the system. For that, we're going to need to find the work done on the system, and we're also going to need to find the internal energy change from A to B to C, because delta U equals Q plus W. So this first part is calculating the work done. and we get a value of negative 6,000 joules. Work for section BC is 0 because it is isochoric. And then we have to calculate TA and TC to find the difference in the temperature states. So going from A to C, what is the overall change in internal energy? So that would give us our delta U of 1500 joules. So we know that delta U equals Q plus W, so 1500 equals Q plus our 6,000, or negative 6,000. So that means that Q must be positive 7,500. Then we are going to do part C, determine the change in the total kinetic energy of the gas atoms as the gas is taken directly from C to A. So this is just looking at what is the temperature at state C, what is the temperature at state A. So recognizing that the change in kinetic energy for C to A is the same as the numerical value of delta U from this part could get us there much quicker, because to go through the whole cycle would have a delta U of 0. So if we had a delta U of 1500 from A to B to C, delta U from C to A is going to be negative 1500, if I remember those numbers. Yeah. So delta K is going to be negative 1500. The last one we have is off of the 2019 exam. This was a lab question. A group of students are using the apparatus shown above to determine the thermal conductivity of a certain type of plastic. A hot plate is used to keep water in a container boiling at a temperature of 100 degrees Celsius. They place a slab of plastic with an area and thickness above the container so that the bottom surface of the slab is at temperature 100 degrees Celsius. They put a large block of ice with temperature 0 degrees Celsius on top of the plastic slab. Some of the ice melts, and the students measure the amount of water collected during the time. The students correctly calculate the amount of energy Q delivered to the ice and thus determine Q over T, the rate of heat transfer. They repeat this experiment several times, each time adding an identical slab to increase the total thickness L of the plastic. Their results are shown below. The students want to create a graph to yield a straight line whose slope could be used to calculate the thermal conductivity of the plastic. For this, I would actually start with an equation. This is the equation that I'm going to be referencing because it has the things that I care about in it. It has the heat transfer rate. It has thermal conductivity. It has the width, the thickness of the plastic. And I'm going to use this to figure out what to graph. This is going to be my y-axis, and 1 over L is going to be my x-axis. Because the thickness is in the denominator, I need to graph 1 over L. I could also, if I really wanted to, graph A delta T over L, but graphing just 1 over L is enough. So label the axes to indicate a pair of quantities that could be graphed. So having our axes labeled, make sure that you include units for your axes labels. On the grid on the previous page, create a linear graph using the values for the quantities indicated in part AI. Be sure to do the following. Add to the data table the values of quantities that are plotted that are not already given. Scaling the axes, plotting data, drawing the line. So scaling your axes linearly so it extends at least halfway over each axis. Make sure that you're including the entirety of the graph paper provided. Make sure that you accurately plot your data and then draw your line of best fit. We then need to use the graph to calculate the thermal conductivity of the plastic, so you're going to calculate the slope. When you calculate slope, I strongly recommend you find 2 points on here where your graph intersects with the axes and circle those points. Make sure that you're not using the same representation you did for data points, and use that to calculate your slope, and then use your slope to calculate your thermal conductivity. The next section, the rectangle below, indicate one potential problem with the setup that could lead to an experimental value for the thermal conductivity that is different from the actual value. So what could go wrong? So really the one thing that could go wrong is we could have interaction with the environment. So if we're in a warm room, the ice could be melting from the top as well as from the bottom. So it could skew the data higher, the heat transfer rate higher, which would skew your answer for your thermal conductivity higher. For a reasonable explanation of how additional energy added or lost could change the experimental value. So you also have to follow through with, if this is true, then what would happen to my data? So my data would be higher or my data would be lower if it were in, let's say, a freezer for some reason, or if it were really, really, really cold out in your lab and you were below freezing. The rectangle below represents a side view of the plastic slab. Draw a single arrow on the diagram to represent the direction of the net flow of energy through the plastic. This one should be pretty easy. It's coming from the hot plate into the boiling water, through the plastic into the ice. Describe what occurs in the plastic at the microscopic level that explains the energy flow you indicated in part C. So the water is moving at a higher average velocity than the plastic, so it is bumping into the particles of the plastic more quickly, which are causing the particles of the plastic to move more quickly, bumping into other particles, bumping into other particles, bumping into other particles. Whenever you're dealing with that kind of transfer of energy through bumping, I'm going to be honest with you guys, use the word jiggle. Physicists love the word jiggle. Carl Sagan made it kind of famous, and physics teachers love Carl Sagan. So if you're talking about these particles hitting into other particles, hitting into other particles, use the word jiggle. It's silly, but it's what works. So energy is absorbed at the lower surface, making the particles jiggle faster or vibrate faster. They then move other particles near them until they reach that energy transfers to the other side. An extra plastic slab sits on a wood surface. With both the plastic slab and the wood surface at room temperature, the student touches each to find that the plastic slab feels cooler than the wood surface. Explain what causes this observation. So indicating that while they are at the same temperature, that temperature is lower than body temperature. So when you put your hand on both of them, heat is going to be drawn from your hand. If it is drawn from your hand faster, you're going to perceive it as being cooler. So the thermal conductivity of the plastic is higher than the thermal conductivity of the wood. Okay, that's going to do it for these 3 FRQ questions. Please let me know if you have any comments or questions.